Hello, welcome to Bedroom Builds at the From Python to Rust series, episode 33, PostgreSQL, coming from the previous episode where we spoke about SQLite. So for Python, the most well-known and DB API 2.0 implementing library is PsychoPG2. That library is already very established and very old and supports lots of stuff. And therefore, this async AI OPG that exists actually uses PsychoPG2 to do the async functionality, because that's part of the PsychoPG2 package actually. And for Rust, we also have a blocking client that is called Rust Postgres, but if you import it into your projects, it will just be called Postgres. And the async version from the same developer that develops the Postgres crate is called Tokyo Postgres. So this is more or less optimized to use the async implementation of Tokyo. And then, as I already mentioned last time, there is an interesting Rust crate called SQLX that will let you connect to, for example, SQLite and PostgreSQL using an async fashion. But it's in strong development, so you could and maybe even should look at it, but I am not covering it in this episode. The data, as in the last episode, is coming from the COVID-19 India API. It is the very same CSV document. And in order to know what we are talking about today, I will jump over to the data. So here we can see the data. On the left, we have the CSV file open, and you can see that this API provides us the columns date in ISO format, and then daily confirmed cases, total confirmed, and so on. Below you see they are comma separated, so here we have like a human readable format, then the ISO date, and then the numbers with the comma separated. On the right, this is my SQL script to import this and start with a clean database. So I'm dropping the tables first. Then I begin a transaction to make sure all of these queries execute fine, and then I commit the transaction. Advantage of PostgreSQL is that those DDL changes actually can be part of transactions. We do a similar trick as we did with SQLite, but here the importing of CSV data requires for you to create a table in the first place with the correct data types already set up. So we have our first column, which is the human readable date, which is of type text. Then we use an actual date, and then we get the integers of all the numbers collected. Then we can use this \copy command to read the file from the local file system where the PostgreSQL client is executed. If you were to remove the \, the copy would actually try to load this file from the server side. If you happen to be on the server while you're running this, both will be equivalent, but this is an important distinction of what's happening with this command. Yeah, we give the file name, then the format, so we use normal CSV, and we tell the importer that this has a header. So in the first line, you can see there's a description of what each column is supposed to be. Since we don't care about the human readable date, we drop the column after we did the import, and then we pre-create our month cases as we did for the SQLite episode. So we can create a materialized view of one of our queries. Let's change over to the code. First, the blocking version. On the left, as usual, we have our Python code, and we start by importing PsychoPG2 and the extras. And I built a helper module because I'm showing off the blocking and the async module, so I don't have to write the queries twice. In order to connect, all you have to do is call PsychoPG2 connect with your connection string. In the real world, you will have a password, and you will very likely use TLS for encryption. This runs locally for a test, so this is why there's not more information given. Then, in order to have more information of the rows coming back from a query, The easiest way to do this is to use, for example, this dict cursor factory. This gives you the option to create a dict with the keys being the column names and the values being the values of the row in a dict format. Otherwise, you will only be returned tuples. Then we are creating this insert cursor to trick the loop further down, then to make the inserts in a separate cursor connection. And we run our first query, the most recovered people, so which day in India is where the most people are recovered from the virus. And then we print it in dict fashion. So there we get our key value output. And here in the bottom section, we write our materialized view. So we delete from month cases, then we run our query, then we print them out, this time in the tuple format. And we can use this to execute our insert query with the correct placeholders. In the case of PostgreSQL, the change here is that these are %s denoted and not a question mark, as they are in SQLite. And at the end, we commit our transaction. On the right side, in Rust, I have here the main function that starts with the client connection, but you are probably wondering where this client is coming from. This time I did not extract a conversion of a row into a string vector. So this is down here. And at the very top, you can see I use the create Postgres. From there, I get the type, client, error, and I'm not using TLS for the connection. Let's go back down to our main code. Since you cannot have default values for function arguments, you have to pass a value. And in order to not use TLS at all, you pass this no TLS enum value. Then we do our query, and same thing. We have to provide every argument, and we provide an empty list of potential arguments that go into a query. We run this, and we get the rows object back. This rows object can then be indexed and used. Here is just a small example of how you would convert the first column, for example, into a date. You will have to import the chrono crate and use, for example, the format naive date, because the Postgres crate implements the from trait from the SQL date into Chronos naive date. If you want to know more about which Rust native types convert to SQL and which SQL ones map to the Rust native types, you can check out the documentation of a PostgreSQL client in. Then I demonstrate how we use the row to a string vector function, and then below we build a Hashmap that actually now gives the same result as if we ran this most recoveries with the dict. In order to start a transaction, we can call this client transaction. The question mark at the end denotes if there is a problem. We error out, which is the return value of our main. And this we can use everywhere. So this is also used here. And of course, when we start the connection, because there's lots of things that can go wrong. Once we have our transaction, we can use that instead of the client. So up here, we use the client query, but here you can see we use transaction query. So from the start of this transaction, we now have the transaction instance available, and here we can run our queries. And for example, as you can see here, we also can prepare a query. So first we delete all entries from the table. Then before we start the loop, we prepare already the query that we want to run. So this in our case is the insert into the table with the 3 placeholders, and I called it insert material view, which we will use down here in the transaction to do the inserts. So here we can use the transaction query result as an iterator, so we can run the for row in the query result, print as we do on the left the string vector, then we get our date, the new cases and the recovered count from the respective columns, so 0, 1, and 2. And once we've done that, we can run our prepared query in our transaction execute. And here we then pass the arguments to fill our placeholders with the correct escape sequences. And after that, we can transaction commit the whole thing. Now let's see if our Rust code works as expected. And I will have to change to pg blocking and cargo run the thing. And it works fine. Now one cool extra feature that Rust provides you is, of course, the borrow checker. So in line 47, we start the transaction. And let's suppose you are about to refactor this code block to make it a transaction because it wasn't before. Then the old code would have at the different locations, like here and here, the client as the variable. So let's suppose you forgot to change that in your refactoring. Then a normal IDE or editor will not quickly notice that because client is well defined, right? So we set it up here, we use it. So here, this will not be highlighted as an unknown variable or a word that is used the first time or something, right? But the compiler knows. So if we now go and try to run this again, then the compiler will complain and tell us that client has already been mutable borrowed, and therefore you cannot reuse it at a later stage because now this is in transaction. So we have to use transaction all the way until we commit. And after we've committed, we can actually use the client again. So let's show that feature quickly. We hop over, we rename this into transaction again. And we run, for example, the delete query at the end. In order to do this, we have to, of course, call this client again. If we now go to the left, if we now run this again, it compiles, it runs, and of course now after we did our transaction, we actually clear everything. So here you can see the advantage of the Rust compiler together with a well-designed crate, because this way you can actually make sure at compile time that your code is sane and does the right thing even before you run it. And that is a very, very powerful feature that I miss very much from a dynamic language like in Python, where you can easily forget to rename a variable or call a function that actually doesn't exist yet. And you will only run into this at runtime, erroring out when you don't expect it maybe. Okay, let's hop over to our async examples. Now those async examples are a bit more complicated. In Python, we import async IO because we need this to run the actual event loop, as you can see here at the bottom. Then we use, again, the PsychoPG2 extras to have our dict cursor, which is here. Then we use the asynchronous client that exists for PostgreSQL called AIOPG, but there's other solutions out there. And again, the helper to have access to the queries that I want to use. Then this becomes a bit more nested because you can use all those context managers that AIOPG provides. So here we set up a context that creates a connection pool to our server with the connection string necessary. So now we have our connection pool. Then we can acquire a connection from this pool. Once we have the connection, we can create a cursor with our dict cursor. Once we have that, we can run, of course, our first query. Since all of these functions and the methods are asynchronous, we have to await to keep the normal execution flow as we had before. So I'm not taking any advantage of having this asynchronous client in this example case. but if you have a good use case on your end, there is a client for you. So after we have awaited the execution of our query, we can fetch all rows, and then we can show the first row. We cannot use a commit. Therefore, if we want to have a transaction, have to begin the transaction with the normal cursor execute and the SQL command begin. And in order to commit the transaction, we use commit at the end. After that, we can delete our monthly cases, run our select. And here you can see we have to use now the async iteration over the cursor's result. And we then put the rows that come out of the query into a list that we've instantiated here. Reason is we cannot use this one single cursor to mix querying and fetching the results out of it, and while doing this loop, also executing the insertion. Therefore, we first collect into local memory the results of every row. Then we go over all of these results, print them to match the functionality of what we had before in our blocking case, and run the insert queries with the data found, again with the %s placeholder instead of the question mark. On the right, we now use async, therefore we have to denote with this attribute. The Tokyo main handler will take care of this. Then we also use the error result type because we are still using the question mark operator or try operator to error out if there are problems. As we did in Python, we have to await the results. The syntax is slightly different, but the idea is the same. There's not too much changes from before, but now instead of just a client, you get back a connection and a client. The reason is explained down here in the comment. So this connection object is needed because it does the communication with the database, and then the Tokyo Postgres handles for you the later down client queries to then actually have a connection available. So we spawn this connection object off. If there is an error, we print it to the user. Once we have done that, we can now run a query. The only difference is we await. Once we've done that, we have the exact same code that we had before. So now in this code, I will explain those two functions, but a bit later. Let's continue further down in our async Rust code. So here we have the output as a vector of strings, and then we have our hash map of strings. So in our transaction, we delete, we prepare the insert query, we start the loop over our select. Then we print in our vector format as we did before. Here again, we split it up into our date, new, and recovered using the respective column values. And then we execute the query with the arguments and we transaction commit. So if you are changing from using Postgres blocking to the async version, because maybe you have to because you're using an asynchronous web server as a backend, then this will actually be fairly straightforward to do. You more or less attach dot await at the end, set up the Tokyo event loop, and off you go. Now let's look quickly at the implementation of those two functions. In order to explain the functions, we have to look a bit at the select query. So the group by month is using the ISO date, but we are, instead of string formatting as we did in SQLite, there is a special function provided by PostgreSQL called the date trunc. It will then truncate the whole date to what you specify. In our case, we wanted the month, and we can then typecast this to a date. In SQLite, as you might remember, we had to string format our date into a certain type of string, and this was how it worked. The advantage here is that we are still dealing now with an actual date. Below, these are just integers, and this now explains my silly way to convert the vector of strings. And if you go to this URL, you can actually figure out those type definitions and how they map to the native types in Rust. Now, the first column that we get is also the first one we match against, so it's type date. And if the type of the column is of type date, we make it a naive date and convert this then to string in order to have a vector of strings in the end. So what's happening here is we are passing in a Tokyo Postgres row, and this Postgres row only would be used if you were to use the blocking crate. Then we go over the columns in the row, make this an into iterator. Then we have here the column index passed into our map. Here we can then match against the column. We can unwrap because we are sure we are doing nothing wrong. We are up here actually going exactly in the range of columns that exist. And then we can ask for the type. We have to use the underscore because the word type is a reserved word in Rust. So the designer of the API called it type underscore. We already went over the line where we match against date. Then the same is true for int4, so a 32-bit integer. This of course maps to i32, and then the int8 is a 64-bit one, and we do that. We convert everything to string, and not happening in our case, but if you were to apply this function to something that has yet other types applied, we use this catch-all with the underscore, and here we just put a useless word to denote that we cannot treat this. When I was cutting the video for the SQLite talk, I realized I was stupid to rewrite the whole loop from the vector, so up here, again to build a hash map, because I can actually use the output of the vector to build the hash map. So how does this work? Well, first we get our vector of strings. Since we want to have a hash map of strings mapping to strings, this is actually easy to use now, because now we can use an into iterator that now zips together with the columns of the row. So here we map the values and keys tuple, key being actually the column name coming out of this row columns iterator. And now we can use the columns name converted into a string, and the value is already from the into iter string. We collect this and we get our hash map string. These functions are the same except for the signature. So these take a Tokyo Postgres row, and the other ones only take a Postgres row. Okay, this was a minimal introduction how to connect and do at least the minimal stuff with PostgreSQL. This is of course a much bigger and wider field because the feature set of PostgreSQL is amazing, and I might revisit this later. So thanks for watching. Coming up next at the From Python to Rust series will be WebSocket servers.